Today, our focus is on critical integrity challenges facing by our hydrogen heating system, which must raise hydrogen from the ambient to 1000 degrees centigrade. This project demands immediate attention because our heating element face two major threats. One is the chemical contamination from the gases like carbon monoxide, carbon dioxide, hydrogen, and nitrogen, and severe element fatigue caused by the wide temperature fluctuations, particularly during a startup and a stabilization. Now, as we can see, the baseline challenge is ensuring the material longevity for our heating element to survive and operate reliably. They must simultaneously withstand a high thermal load and extreme reducing environment inherent in heating hydrogen gas. Given the 1000 degree centigrade target, the element itself will operate significantly hotter, requiring material capable of 1200 degree centigrade or higher element temperature. In the pure hydrogen environment, if we fail, the result premature creeps and formation or scaling. Now, to select the right material, we must meet three key requirements. The first, maximum permissible temperature. The material must handle element temperature exceeding 1200. Second is the oxide stability. The material must form a dense adherent oxide layer that resists gas diffusion, ensuring long life. And the third and the final one is the mechanical strength. The material needs sufficient grip strength to prevent physical deformation like bunching or sagging under high thermal load. The introduction of contaminant like carbon monoxide, carbon dioxide, hydrogen, and nitrogen fundamentally change the corrosive atmosphere. This crisis introduces a specific catastrophic failure pathway, namely two dual chemical threats, green rot and carburization. These are the two biggest damage creators. We must specifically address how carbon bearing gases compromise our system integrity. The green rot threat is specific to nickel chromium alloys like nicrothal. When used in furnaces containing carbon monoxide protective gas atmosphere, this type of corrosion develop rapidly within the critical temperature window of 800 degrees centigrade to 950 degrees centigrade. Therefore, it is mandatory precaution that nickel chromium material must not be used in carbon monoxide atmospheres. Coming to iron, chromium, aluminum alloys, which are very superior and required in this industrial furnace scenario, are best to use. Carburization is the risk of high carbon activity leading to accumulation of free carbon on the element surface. Here, the material selection is our mitigation strategy. The protective aluminum oxide film that form a FeCrAl aluminum act as an extremely efficient barrier against this high carbon activity. Specifically, the superior alloy APM is highly resistant to carburization, a critical factor if our hydrogen is mixed with any carbon bearing gases. The operational reliability include wide temperature fluctuation, particularly during startup and process adjustment. This thermal shock is highly destructive. A rapid temperature fluctuation significantly reduce the operating life of heating elements. The mechanism is simple. The thermal cycling stresses the protective oxide layer and the underlying metal, accelerating creep and deformation both. So this means material robustness alone is not enough. A strict operational stability control is absolutely necessary. Now coming to combating both chemical and thermal stresses. As we have just earlier discussed, we rely on ferrochromium aluminum alloys as our preferred choice. Advanced ferrochromium aluminum alloys can handle a maximum permissible element temperature of 1400 degrees centigrade in hydrogen. Critically, ferrochromium aluminum provides a significant longer life, 2 to 4 times compared to nickel chromium material, and we have already discussed in the preceding slide that if we have a contamination of any carbon monoxide and carbon dioxide and nitrogen, then we should not use nickel chromium material. So this is and we must have to use nickel chromium ferro chromium aluminum, which provide 2 to 4 times longer life, as we have just discussed. So this is due to their excellent dense non-spalling oxide layer, which is resilient to gas diffusion. So thus, for maximum assurance, we must select the powder metallurgical ferrochromium aluminum alloy APM. APM offers a improved hot strength, resulting in better form stability that actively prevent bunching and creep both. The creep strength of APM is at elevated temperature is comparable to nickel chromium 80-20. This advanced material provide longevity, resulting in life expectancy at 1000 degrees centigrade, that is more than double that of nickel chromium wire. Now coming to the mitigation strategy, and out of many, the first one is about the mitigation by the pre-oxidation protocol. And as we have already discussed in the preceding presentation also, that this pre-oxidation protocol is very much necessary to enlarge the life of this heating element. This is that's why called non-negotiable activity. Ferrochromium aluminum element operating in a complex atmosphere can act in a carbon dioxide and nitrogen also, and for the which it must be pre-oxidized to establish the necessary protective oxide layer. The mandatory protocol require performing pre-oxidation in air at 1050 for 7 to 10 hours prior to any use in reducing environment. By doing this, there is a formation of a dense layer which resists the gas diffusion, and furthermore, regular reoxidation must be carried out at a suitable interval to maintain the integrity of this critical protective layer. So design must be amplify the material strength. First element, life, is directly related to material thickness, so we must select thick wire or strip. Second, we use freely radiating design like rod over bend for maximum surface load. Third, for ultimate isolation, use seamless extruded radiant tubes such as APM tubes, which isolate the element from the gas flow, enhance longevity, and eliminate welded failure portion at different points, thus preventing contamination of the process gas. Prevent the contamination of the process gas. Now coming to the mitigation strategy number 3. So to actively combat the temperature fluctuation, we must employ advanced electrical control system, and especially thyristors, uh, thyristors, and which can have got a which can provide an even temperature and minimize rapid changes. This stability directly maximize element lifespan. Additionally, if elements are placed on a furnace base, we must use hearth plate made of material with a good thermal conductivity like silicon carbide to minimize the temperature difference, and use separate thermocouple to prevent localized overheating. So we are now coming to the summary. So to summarize the path forward, the threat of contamination as we have discussed earlier, is countered by the mandatory selection of APM, ferrochromium aluminum, for its superior carburization resistance and its ability to avoid grain ROT that we have discussed in the preceding slide. The threat to oxide integrity, hydrogen, nitrogen, is countered by mandatory pre-oxidation at 1050 that we did, and so there is a way out for it. That is pre-oxidation at 1050 for 7 to 10 hours, which establishes the necessary dense barrier. And finally, the threat of thermal shock creep is countered by employing thyristor control and using thick material which minimizes fluctuation and ensure hot strength. So the integrity of this critical 1000 degree centigrade heating project depends entirely on our serious and detailed execution of these strategies. The difference between proper execution and failure is a factor of 2 to 4 times the expected life. We must treat the three scientific protocol as non-negotiable, the mandate non-negotiable mandates, and what are those that we have already discussed? We have to use APM, ferrochrome aluminum material, execute pre-oxidation is must at 1050 for 7 to 10 hours, and implement thyristor control. Our commitment to this detail is the only way to unlock the extreme longevity required for this system.